All right. So in the last session, we discussed about reflection of light, isn't it? So as per the law of reflection, we say that it is the bouncing back of light. That is the idea. And the laws will be stated such as the angle of incidence is equal to the angle of reflection. And the second law will be incident ray, reflected ray, and normal. They all lie on the same plane, isn't it? Okay. What is the
Yeah.
example for reflection or any application for reflection? There is a periscope. Can you just explain what is the meaning of periscope here quickly?
It is what to see over or around objects.
Okay, and what is the angle that it needs to be projected here? As you can see, 45-degree. Okay, so when you project an angle of 45-degree, then only reflection occurs inside the periscope, and the light ray will reach the human eye. That's how you're able to see over the things, right? Over the above the water surface. This is the application of reflection. Next, moving towards refraction. Can you tell me what is the definition for refraction of light?
Refraction, it is when light that travels through many different transparents,
Yes, it is.
including air, glass.
Okay. In that case, what are the things you're going to observe? As you can see over here, there are certain rays which is bending. So the refraction is all about change in its path of light when it is traveling from one medium to another medium. So in this case, the ray of light is traveling from rarer medium and it enters into the denser medium, isn't it? So there is bending taking place. Okay, so based on this idea, can you state any two rules whenever the ray of light travels from rarer to denser? What happens to the normal? Will it go towards the normal or away the normal?
It will go away from the normal.
Are you sure, Mohammed? This is a
I'm sure.
transparent medium and you are projecting a laser light. Okay, that is monochromatic light. As it enters through this medium, we know that there is change in its path. Again, when it is leaving the transparent medium, it is moving away. At this point, normal can be drawn. Okay, so from this observation, what do you notice, Mohammed? When it enters from air medium to glass medium. Okay, this is glass medium. What's happening to the ray of light? That is the rule. Look at this.
It's it's changing its direction.
It's changing its direction. Good. And you can see that the direction of the path of light, it is moving towards a normal. Don't you think so?
Yeah.
Yes. So first rule, please remember this rule. Whenever a ray of light traveling from air to glass, the ray of light moves towards the normal. Very important point this is. Moves towards normal, that is capital N. This is first rule that you have to remember. Next rule, whenever a ray of light which leaves the medium, that is from denser is glass, from glass medium, now it is traveling or emerging out into the air medium. So what's happening over here? Can you explain? The ray of light, is it moving away or is it coming closer to the normal? What do you see?
Uh, it's moving away.
Exactly. So it is moving away from the normal. Okay, moving away. So this is two rules you have to remember, Mohammed. Please don't forget this. We have to apply this in experimental and investigation type of questions, because whatever we are discussing here, we are going to solve past papers. During the past papers, you should have this basic knowledge. Then only we can easily be able to figure out whatever the expectation will be from the question. Is that clear with you?
Yeah.
Okay. So now let's move. We have completed refraction of light and we saw many applications of refraction. One is the rainbow. What you can see here, it is because the bending of light, you can see a beautiful rainbow which consists of 7 colors. That is vibgyor: violet, indigo, blue, green, yellow, orange, and red. All right. Okay, next is um yes, when a ray of light enters directly on the medium, as you can see here, it is projected 90-degree. What happens in this case? What about the refraction
Uh,
of light?
it doesn't move. It's a straight line.
Yes. So the case here is when a ray of light is projected at 90-degree, there is no refraction. There is no change in path. It travels in the straight line itself. All right. So only in the case of 90-degree. Okay, so moving to the next one. What do you mean by refractive index?
Refractive index
Mhm.
is when different materials that can bend light by different amounts.
Exactly. Good. How would you use this in an equation? How would you read this out?
Uh, Refractive index is sine I over sine R.
Yes, sine I over sine R, but in detail, I will say you the sine I is there, right? It is actually the speed of light in air medium divided by speed of light in denser medium. So there are two comparison that is taking place from one medium is in the numerator and the other medium is in the denominator. With the same phenomena, as you can look into this total internal reflection, just parallel to this, a ray of light, in this case it is traveling from denser medium and it is coming out of the rarer medium, that is air medium. If you want to compare this refractive index to this diagram, you would say that the sine I in the numerator will be the speed of light in the glass medium divided by the speed of light in the air medium. You got my point?
Yeah.
That is refractive index. It is the ratio between two different pair of media. Okay, so done. And we also worked out how to solve and find the refractive index of a glass, and even you can find the refractive index of a diamond, any material, kerosene, petrol, oil. So all these will have different values. They are not same. That is one thing that you have to remember about refractive index. Then we saw investigate the refractive index for a glass, and alhamdulillah, you said that you have already done this experiment earlier, right? What do you observe from this? You observed that the ray of light changes its path, all right? And you saw that for the list of angle I and angle R, there were different values. When it is entering into the rarer medium, into the denser medium, you saw the angle of refraction to reduce. And when it is moving away from the denser medium, the angle of refraction will be greater because it is moving away from the normal. All right, so that is the application. Now, moving to the main, the last part of this topic will be total internal reflection. Did we start this in the last session?
Yeah, a little bit.
Little bit, right? Yes. What do you mean by
Wait,
total internal reflection?
it is it is when a ray of light with a small angle of incident is when incidence of angle or small angle of incidence
Mhm.
passes from glass to air into air.
Yes, yes. And the condition of total internal reflection is a ray of light must and should be traveling from denser medium, not from rarer. Okay, it should start from denser and it has to move into the rarer medium. So that is one condition. Okay, next is, as you can see here, when a ray of light falls on an object, there is reflection taking place, there is refraction taking place, and absorption also will occur, but absorption is not seen dominantly over here because it has been absorbed. All right. Now coming to this total internal reflection, how can we able to reflect complete light inside the medium itself? We don't want it to refract and bend light. Okay, we want it to internally reflect. So for that, we have to follow this. As the angle of incidence in the glass increases, the angle of refraction also increases until it reaches a special angle called the critical angle, which is denoted by C. Okay, so they're already mentioning that it is a special angle for which the angle of refraction now is 90-degree. As you can see here, at some angle, we don't know what is this angle like. Maybe something here, when it is projected, we saw that uh, not here. This is the best example. Yeah. So in this case, we saw that the angle of refraction is 90-degree. That is along the surface of this medium, isn't it, Mohammed? It is on the straight line, and reflected reflection is already happening. So this is called as critical angle. So the critical angle is the smallest possible angle of incidence at which light rays are totally internally reflected. Did you understand this sentence?
Yeah.
Okay, so it is the smallest possible angle for which the light ray is totally internally reflected, not refracted, it is reflected. Okay, so moving with this idea, we can say that when I is greater than the critical angle, so angle of incidence, that is, or the incident ray which is projected into the denser medium, is greater than the critical angle, all the light is reflected at the boundary, no light is refracted. The light is totally internally reflected. For this to happen, what is a condition? Angle of incidence should be greater than the critical angle. Please remember this point. For total internal reflection, angle of incidence must and should be greater than the critical angle. Then only this total internal reflection is possible. Otherwise, not. Did you understand?
Yeah.
Okay, so with this note, let's move further. Okay, so now we are going to investigate, okay, how this total internal reflection occurs. So this investigation type of question will come in paper 2P. So when we are going to solve past papers, so in 2P papers, will the idea of 2P paper will be basically you are going to conclude something. You're going to look at the observation. You're going to derive the values. If not, they will give you the values, but you have to make judgments, you have to make conclusions. That will be 2P paper. It's an interesting paper. It has only it consists of only 70 marks, but you need to be very careful while solving and using physics terms. Okay, so look at this now. In this case, they're trying to investigate total internal reflection. Okay, in what way are they going to investigate? So you can investigate total internal reflection in the laboratory using a semicircular glass block and a ray box. Okay, so this is a semicircular glass block. Why it is a semicircular? Because it is a half circle, and a ray box which projects ray of light. As shown in figure here, a ray of light is directed at the center of the straight side of the block through the curved side. Look at this. How are they projecting the light? They are projecting the light at the curved side. All right. So we do this because the incident ray will then always hit the edge of the glass block at 90 degree. So there is no refraction effects to take into account as the light goes into the block. Okay. Now, by carefully increasing and decreasing the angle at which the ray strikes the flat edge of the glass block, we can discover the smallest angle at which most of the light is refracted along the edge of the glass block. This angle is called as critical angle. Okay, so why are they doing this experiment? They're doing this experiment because they want to know what is the smallest angle possible for this to occur. That is, the refraction should be 90 degree. And they discovered that for light passing from glass to air, again from the denser to rarer medium, the critical angle is typically 42 degree. And the critical angle for light passing from water to air is 49 degrees. So you have to remember critical angle from glass to air is 42 degree, and from water to air it is 49 degree. Is that clear, Mohammed?
Yeah.
Okay, in this case, what's happening? If the critical angle is 42 degree, then only we can able to get refraction angle is how much? 90 degree. Otherwise, not in case of glass medium. So we have discovered critical angle to be 49 degree. So you 42 degree, you have to remember this value. Next is they are going to write this in an equation. So the critical angle for a particular medium is related to its refractive index by this equation. That is sine C is equal to 1 by n. What does n represents here?
N is normal.
No, capital N is normal. The small letter n is?
Refractive index.
Yes, small letter n is refractive index. Very good. Okay, so this is a formula for critical angle. Okay, so we have already done this question, isn't it? So you have to apply the formula sine is equal to 1 by n. They're asking, they're what is that they given in the question? They've given the refractive index of a type of glass is 1.45. So 1.45 mentioned in the denominator because it is a refractive index of a glass. Calculate its critical angle. So C, whenever you're going to calculate C, this sign when it goes to the right hand side, what does it become, Mohammed? What does it
Uh,
change when sign
the
goes?
it will be sine inverse 0.69.
Very good. So when sine goes to the right side, it becomes sine inverse. And sine inverse of 0.69 will be 43.6 degree. Isn't it? Are you clear up to here?
Yeah.
That's perfect. Okay, now moving to the next new topic.
So,
Yes,
we already did this.
we did this, right? Yeah. So we did up to here. Now we are going to look into the prisms. Did we start prisms? No, right? Okay. So now we sometimes use prisms rather than mirrors to reflect light. The light is totally internally reflected by the prism. Okay. So what is a prism now? We're going to look into it. Do you have any idea what is a prism?
A prism, I think it's like a 3D shape.
Yes, it is like a 3D triangle. Okay. So can you define a prism? How many surfaces does it has?
Surfaces? No, not sure.
Okay, as you can see here, the front side is one surface, the back side is second surface, then rectangle, this side third surface, and this side fourth surface, and the base is fifth surface. So total it has five surfaces. Did you understand?
Yeah.
So a prism is a transparent medium bounded by five surfaces. Front side one, back side two, rectangle three, then this side rectangle four, and the base is five. So total five surfaces it has. You can actually see this in reality also. If you have a prism, it is like keeping it on the paper so that paper do not fly due to wind, right? So they're going to just keep it as like a holder, right? So the prism, what is a specialty about this is it can reflect light totally. It can reflect, so the what is the total internal reflection occurs in prism better than mirrors. Now we are going to look how is that. All right, okay, so we can see how it is reflected. Okay, so look at this now. So practical, investigate total internal reflection in prisms. If you shine a ray of light into a prism, as shown in figure 12.3, look at this, it will strike the far surface at an angle of 45 degree. So you're projecting ray of light as it enters the prism, it is going to reflect at what angle? At 45
Uh,
degree. Is going to strike at 45 degree, and the critical angle for glass is about 42 degree. So now what do you see here? The incident angle is 45 degree, but the critical angle for the glass is 42 degree. It means the angle of incidence is
because
greater than critical angle,
yeah,
then only total internal reflection occurs if this angle should be greater than critical angle. So the ray of light will be totally internally reflected. Yes, this is the condition. Angle of incidence must be greater than the critical angle, then only totally internally reflection occurs. You will see this, you will see therefore that the ray will be reflected through an angle of 90 degree. Okay, so as it enters, it reflects with an angle of 90 degree. So this is the case that you have to remember through a 90-degree prism. Will you be able to remember this, Mohammed? Through a 90-degree prism, case one. Okay, make a note of it. Prism is a
yeah.
transparent medium bounded by five surfaces. That will be the definition. And the next thing is case one. Case one will be when a ray of light is projected into a prism at an angle of 45 degree. At an angle of 45 degree, it will reflect at an angle of 90 degree. It will reflect at an angle of 90 degree, in which case through a 90-degree prism, or you can say a right angle triangle prism. A right angle triangle prism. Okay. If you finish making a note of it, let me know. It is important because you have to remember this and apply this knowledge while solving problem based on prisms. They will not tell you over here what is the reflected angle. They will only say that the angle of incidence is 45 degree. They will expect you to write what will be the reflection of light. That time you have to remember this concept. Okay, so when it is projected at 45 degree, in the case of total internal reflection, the angle of reflection can be 90 degree. Is that clear?
Yeah.
Okay, so with this note,
I just need to take down the the notes.
yes, please. So you can write down 45 degree is the angle of incidence, and the critical angle for the glass that we have already found from the previous experiment is 42 degree. We have discovered this, especially in the case of glass to air, whenever a ray of light traveling. So when the incident ray is 45 degree, there is total internal reflection taking place at an angle of 90 degree. That's it.
Mm.
That will be the first case. Now looking into the second case. As you can see here, they have changed the direction of the ray of light. Here they have projected at a side, that is the adjacent side of right angle triangle. Sorry, opposite side of the right angle triangle. Over here, they are projecting at which side of right angle triangle, Mohammed? What is this side called?
It's called a line segment.
In a right angle triangle, we were learning trigonometry, right?
Oh,
This side, what is it
oh
called?
wait, that side. Wait, six. That's Hypotenuse.
Very good. So the longest side of a triangle is the hypotenuse. Now the ray of light is projected on the hypotenuse. Let's see what's going to happen. So if you shine a ray into the prism as shown in this figure, the ray will be reflected through an angle of 180 degree. That is, it will go back in the direction from which it came. Okay, so if you directly project at an angle of um, at a certain angle of 180 degree, a straight line over here, uh, into this over the hypotenuse, you see that the reflection of angle, what's going to happen, there is a mirror over here and there is a mirror over here, so it is going to reflect and come back to its direction. So the angle of reflection will be 180 degree in this case when it is projected over the hypotenuse through a 180 degree prism. So through turning through 180 degree using total internal reflection. And this application is very important in the case of periscope. Okay, so even in periscope, the ray of light enters and it will reach to the observer's eye. So this idea is used in periscope. It is used in optical fibers. We're going to look into this case where we apply this. Till here, if it's clear, let me know.
Done.
Done. Okay. So what did you understand from these two experiment, Mohammed? These two experiment in your own words, you can say.
Yeah, in my own words, they both equal. If you could see 45 in the first one, they show 45 degrees, 45 degrees, 45 degrees, 45 degrees.
Mhm.
All of those add up to 180 degrees.
Okay. In this case,
And wait, the first triangle is an equilateral triangle, and the second one is an isosceles triangle.
have they mentioned anything over here as such? They haven't mentioned any which type of a triangle is this. They're only proving that
It's a right angle triangle.
yes, it is a right angle triangle. They're only saying that if you project a ray of light at an angle of 45 degree, what will be the angle of reflection? It will be 90 degree.
Yeah.
Okay, in this case. Now in the second case, if you project a ray of light at a 45 degree angle, but towards the hypotenuse side, it will reflect and come back to its own direction from where it is projected. So forming an angle of 180 degree. As you can see this, it will be 180 degree. So this will be the second case. And we're going to look into the application of these two. Okay, so now we'll see using total internal reflection, the prismatic periscope. So periscope, as we already learned, that it was used to see over objects, right? So that is, if people are under the water traveling in a submarine, they can see what's there above the surface of water with the help of periscope, because it will reflect light internally. Okay, and here they are saying prismatic periscope, so that means they're using prisms in a periscope. Okay, so the images produced by prisms are often brighter and clearer than those produced by mirrors. So remember, mirrors can also produce images, virtual images, but not as much as brighter than prisms. Prisms produce much better pictures than periscope. That's why we use prisms in binoculars. We use prisms in many aspects. Let's see into that. So a periscope that uses prisms to reflect the light is called a prismatic periscope. Yes, make a note of this, Mohammed. What is the meaning of prismatic periscope? It is a periscope that uses prisms to reflect the light. That uses a prism to reflect a light. To reflect the light is called a prismatic periscope.
Okay.
Finished?
Oh, no, no, almost.
Okay.
Done.
Done. Okay. So we are using a prism in a periscope that is called as prismatic periscope. Next, they are projecting light and it passes through the surface AB. Look at this periscope. Okay, so people who are there under the water in submarine, they can able to view objects over the above the surface of water. That is, they're able to view this boat. Okay, how are they able to view this? Because light is entering into the periscope from the outside, right? From the sun, the light enters at an angle of 90 degree. That is a straight line. So when it enters at a straight line, we know that refraction will not happen because it is at 90 degree. You only said that case, right? If it is a 90 degree, it will travel in a straight line. So it enters with an angle of 90 degree, it passes straight, but on at this point, so light passes through a surface AB of the first prism at 90 degree, and so does not change direction. It is undeviated. Till here we have understood it is undeviated. But after that, it then strikes the surface AC of the prism at an angle of 45 degree. Now look at this. When it is going to fall into the prism, that is AC is a prism, it is going to reflect at an angle of how much? 45 degree. And the critical angle for glass is 42 degree. Prism is a glass. So the smallest angle is 42 degree, and 45 degree is the incident angle, which is greater than the critical angle. Then only reflection can occur. So the ray is totally internally reflected because it is greater than the critical angle, and is then turned through 90 degree. It travels in a straight line and it enters through the other prism, other glass into the straight line, and it passes undeviated because 90 degree, isn't it? Next, when it leaves the first prism, the light travels to a second prism. Look at this. It is traveling along a straight line. The second prism is positioned so that the ray is again totally internally reflected. Now they have kept a prism in such a position that it is going to totally internally reflect the ray of light again, and the ray emerges parallel to the direction in which it was originally traveling. Look at this. The incident ray, which was sent into the prism, and the reflected ray, which is emerging outside the prism and entering human eye, these two lines are parallel. Are you able to make out from here?
Yeah.
Right, so these two are parallel. And what you need to remember, Mohammed, here is, in case of prismatic periscope, AC is one prism and this is another prism. So they're projecting a ray of light at 90 degree. It will pass undeviated. It will travel along a straight line, and it will enter into the second prism, again traveling in a straight line. But at the second surface, it is going to totally internally reflect. The reason is because the angle of incidence is 45 degree, which is greater than the critical angle 42 degree, and hence it reaches to the person's eye. Did you understand this?
Yeah.
Okay, so that's it about uh, total internal reflection in a prismatic periscope. Easy, isn't it? Will you be able to remember that?
Yeah.
Okay. You want to make any notes, or you have this textbook? You have, right? You have to just uh, copy down later. You can easily write down this. But only one condition, remember, the angle is 45 degree, then only reflection is taking place. What is the reason for this, Mohammed? Why total internal reflection takes place at 45 degree?
Because the critical angle must be less than the incidence angle.
Very good. Very good. MashaAllah, you have understood then. Okay. So critical angle is 42 and the incident angle should be greater than the critical angle, that is 45 degree. Then only total internal reflection is possible. Now let's see its applications. Where are we going to use this total internal reflection? As you can see here, bicycle and the car reflectors. Have you noticed these things anywhere? Car reflectors,
Yeah. Yeah, car reflectors, yeah.
right? So what is the purpose of installing this car reflectors, Mohammed, on the road?
Uh, well, it's used for there's headlights, which in case at nighttime they use it to see the road.
Yes, exactly. So in the during the night time, where there is not much light, so these reflectors will spot the road. Okay, so that means there is a divider. Be careful. Okay, so they can use a reflector to reflect light, and it is just like an indication for the person traveling. Okay, now look at this. So as you can see here, they are projecting a ray of light at an 90 degree, and it will come back to its position. So this prism is basically reflects an angle of 180 degree. Okay, because it is coming back to its own position. Okay, same mechanism what we learned earlier is happening in the case of a bicycle reflector. Have you noticed behind the cycle also there are reflectors, right? So
Yeah.
where people can notice them. Okay, So here, what's happening? Same light which is projected. Look at this. It is reflecting. It is passing through 90 degree. It is reflecting at 45 degree, and it is coming back with an 180 degree. So these two lines are parallel. Same thing is it's happening throughout the event, and that's how you can able to see the bicycle on the road. Next is light entering the prism in figure 12.16. Okay, this is the thing. Is totally internally reflected twice. First it goes back, it hits over here first time, then second time, and come back. So it reflects twice. It emerges from the prism traveling back in the direction from which it originally came. Don't you think so? When it
Yeah.
is entering and it is coming back to its original position. That is only this speciality about prismatic periscope, as well as the reflectors. Okay, the light has to come back. The same thing takes place in car headlights also. All right, so this arrangement is shown in bicycle or car reflectors. Okay, so reflectors like these can save lives. Don't you think so?
Yeah.
Okay, now look at this. In figure 12.18, binoculars. Binoculars are what kind of a devices, Mohammed? Why do they use this?
Just to see what's really far ahead.
Yes, what's there over a long distance, isn't it? Binoculars. What is the difference between a binocular and a telescope? Any idea?
A telescope. I
Mhm.
think it, I think they're both the same. I'm not sure about binoculars and telescopes.
Okay. The idea is basically to see distant objects, right? So binoculars will reach up to a certain limit value where it cannot be crossing our Earth. All right. Whereas telescopes can be used to see in very, very far objects, even the planets, stars, you can able to observe them. Don't you think so? So telescopes can travel over longer distances than binoculars because they're using much greater advanced method in telescopes, that is different type of reflectors. But in binoculars, look at this. Binoculars also make use of total internal reflection within prisms. So they're using these prisms inside a binocular. Did you know about this? There are prisms installed in a binocular. What, Mohammed?
Yeah, I think so. I'm not because they can create. I'm not sure.
Yes, so you can remember now that in a binocular they use prisms. Okay, so each side of a pair of binoculars contains how many prisms? Two prisms. Look at this. Each side two prism and another side two prism. Total four side maybe. So why are they using these two prisms? To totally internally reflect the incoming light. As a light passes through this, look at the direction of the light. So the sunlight will pass in this direction. It will move with an angle of 90 degree. It will not deviate. Again, it will reflect at 45 degree, again 90 degree, and hence it will follow total internal reflection and basically come back to the original position. As you can see here, look at this. These two lines are parallel with one another. All right, so this is the same mechanism taking place. So without the prisms, binoculars would have to be very long to obtain large magnifications and would look like a pair of telescope. Okay, so without the prisms, what's going to happen? Binoculars would have to be very long to obtain large magnifications and would like a pair of telescopes. So if prisms are not there, then it would be like a binocular, like a telescope, where it needs to be long to see the magnification, to see enlarged objects. Magnifications means enlarged objects. Okay, now optical fibers. What is this optical fiber? One of the most important applications for total internal reflection is the optical fiber. Okay, so optical fiber is what? This is a very thin piece of fiber composed of two different type of glass. So when two different type of glass, when they are combined, it forms an optical fiber. The center is made of a glass that has a high refractive index, surrounded by a different type of glass that has a lower refractive index. As you can see over here, all right, so there is a lower refractive index on the upper, and inside this it is having a higher refractive index. So when two glass are combined, it forms an optical fiber. Did you understand, Mohammed, what is an optical fiber?
Yeah.
Okay, so two different material of glass combined together. Okay, my question to you, do you think spectacles are optical fibers?
I think so.
Right, so because even in spectacles, there are short sightedness, long sightedness, which uses concave mirrors, which uses convex lenses, right? So Double concave and convex lenses also will be there. So in majority of the case, there will be two different layers which is formed to spectacle. All right. So optical fiber will be in that category. Spectacles can be in the category of optical fiber. Okay. Now let's see a different application. Okay, they're just explaining about optical fiber, as you can see here. Okay, look at this, some kind of a bright light. So as the fibers are very narrow, look at this, they're very narrow. Light entering the inner core always strikes the boundary of the two glasses at an angle that is greater than the critical angle. So when the angle is greater than the critical angle, then only total internal reflection is possible. That means it needs to be minimum 45 degrees or else at least 42 degrees, so that it should be greater than critical angle and total internal reflection takes place, and we can able to see this beautiful color of light. So no light escapes across this boundary. The fiber therefore acts as a light pipe, providing a path that the light follows even when the fiber is curved. All right. So as you can see over here, next is large number of these fibers fixed together form a bundle. Bundles can vary sufficient light for images of objects to be seen through them. If the fibers are tapered, that is narrower at one end, if it is narrower at one end, it is also possible to produce a magnified image. Have you noticed any kind of a thing like this, Mohammed, where the lights are very narrower at the end, you can able to see the bright image? Something like fairy lights, something that sort of a thing.
Yeah, is it like in plants?
I'm sorry, what?
Is it like I'm not sure. Um, I don't know. I've seen these before, but I don't know where it came from. It was.
Mostly in carnivals and all, in carnivals, in events, uh,
Oh,
right, you see these type of things, right? So basically this will produce much brighter image at the end. All right, so it is a magnified image. Next is figure 12.22. So where is 12.22? Look at this. This is called as endoscope. It is very important in medical science to see what's there inside our body. So they're going to pass this through our throat. Okay, and we're able to see inside what's there inside our stomach and all of that. Okay, so figure 12.22, this is the figure, shows an optical fibers in an endoscope. The endoscope is used by doctors to see the inside of the body. For example, to examine the inside of the stomach. Yes. So when you're going to project this inside the throat and it reaches to our stomach, and we can able to get a clear picture of our stomach. So endoscopes can be used by engineers to see hard to reach parts of machinery. Yes, we can even use this in the case of machinery as well, because certain parts of the machine where it's difficult for person to view it, so they are going to pass some kind of a narrower tube like this, an optical fiber, just like an endoscope. All right, to view inside the parts of the machinery. Next is light travels down one bundle of fibers and shines on the object to be viewed. Then light reflected by the object travels up a second bundle of fibers, and image of the object is created by the eyepiece. So at the end of the day, we are going to get image on the eye. All right. So did you understand what is the meaning of endoscope here?
yeah.
Okay, so by using optical fibers to see what they're doing, doctors can carry out operations through small holes made in the body rather than through large cuts. This is called keyhole surgery. Okay, this is less stressful for patients and usually leads to a more rapid recovery. Don't you think so? It's so important, Mohammed. Or else back then, when they didn't have all this type of technology, people, doctors used to cut human beings over large pieces, and to stitch it back, it is going to be very difficult and much more painful, right? So with narrower hole, with lighter hole, you can able to pass these and can view things inside our body. Okay, so it's a very important phenomenon, don't you think so, in the endoscopes?
Yeah.
Okay.
It's like
Next,
they're used for like doctors to scan like throats and stomach.
yes, to see our stomach, as well as the name for this is given as keyhole surgery. Why keyhole surgery? Because what is the reason for to name as keyhole?
And make a recovery.
It is very small, very narrower, right? There is no much large cuts. Through a narrow hole, they're going to pass inside our body. That's why it is easy for us to stitch it back, not for us, to the doctors to stitch it back. Okay. Next is optical fibers in the telecommunications. So in telecommunications, how we can able to use this? So modern telecommunication systems use optical fibers rather than copper wires to transmit messages as less energy is lost. Electrical signals from a telephone are converted into light energy produced by tiny lasers, which send pulses, that is, small amounts of light, into the ends of optical fibers. A light sensitive detector at the other end changes the pulses back into the electrical signals, which then follow into a telephone receiver earpiece. So they're using it in telecommunications by using the same mechanism of reflection of sound over there generally. Okay, we can study, that is our next topic. Okay, how it is used in telecommunications, that is our sound concept. So we have completed light. Mohammed, you have any doubts in this? Any
No,
questions till here? No
I'm
questions.
recording lessons so I can review it.
Okay, so there are no doubts over here. So by this note, I would say that the light is completed. Next, we have to just look into what is sound, how sound is produced, and what is reflection of sound. Very important in this is sonar submarines. It's going to detect sound. It is important, and there are certain sums based on this, so that we have to concentrate here. Reflection of sound and audible range, loudness. That's it. Okay, very short topic here. Okay, now I just saved one video over here that I wanted to show about reflection of sound. Okay, before the reflection of sound, I just want to show what we have done now. Okay, I will just finish this.
Through a prism. 1. Description. 1. A, B, C. Be the principal section of a prism. 2.
Okay, one more thing, Mohammed. Principal section. The meaning of principal section of a prism is the front side of the prism, A, B, C. What you can see, right? The front side, that is called as principal section. Remember that?
A, be the angle of gamma. 3. Mu,
Sorry, can you turn up the volume?
Volume is it? Okay. Mm, it's actually high. What about here? Speakers is 90. Okay. I think there's someone struggle from
Because
it.
refraction index of the material of the prism. 4. PQ, be the incident ray. 5. I1, be the angle of incidence. 6. I2, be the angle of emergence. 7. I1 minus R1, be the angle of refraction. 8. I2 minus R2, be the angle of refraction. 9. D, be the angle of deviation.
Okay, that's it. So, Mohammed, they have just given one basic idea about what is a prism. So, prism is nothing but whenever we are going to pass a ray of light. I'll just explain it to you over here. So, this is the principal section. What do you mean by principal section, Mohammed?
I didn't hear very well, but I think it's I didn't hear nicely,
It is the front side of the
but
prism.
yeah, the front.
Yes, it is the front side of the prism called as principal section. Now we are going to project a ray of light into the prism here. So a ray of light, laser light, for example, it is entering into the prism and it is changing the path. Again, it is emerging out by changing the path. Now, where are the normals? Normals are over here and normals are over here. And especially this angle is called as angle of prism. So the main angle of prism is angle A. So this is angle of prism A over the principal section. All right. Now this is I, that is what I represents for incident ray, and this is angle of refraction. This is angle of incidence. Okay, same R will be traveling over here, and this will be emergence. So I2, this is I1, this is R1, this is R2. Okay, now when in suppose in the case of absence of prism, if there was no prism, then this light would have traveled along a straight line. Even this light would have traveled along a straight line. Okay, so over here they are saying there is a deviation. This is angle of deviation. Deviation means how much, with how much of angle they have deviated from its path. Okay, I will explain you in detail, but fortunately you don't have this topic right now, but this is just an idea about a prism, what's happening. Did you understand this? At least the
Yeah.
basic part of it. Okay, so this is about prism. Now, what is total internal reflection? Okay, I want to show you one half part from your applications. Where is that application? I was watching this. Okay, from here. Okay, look at this. This is reflecting prism.
Let's look at the following incident ray. It hits the glass at an incident angle of 0. Therefore, no refraction would happen and the light will just continue straight until it reaches the other surface. At this point, we need to draw a normal line and find the angle of incidence, which is in this case 45 degrees. This is by following the geometry of the shape. Since this is a right angled triangle, the incident angle would always equal the angle in the top corner of the prism. Now, since the angle of incidence is more than the critical angle of glass, which is 42, total internal reflection would happen as shown, and then the light will just continue moving straight away from the prism. The oblique surface of the prism acted as a mirror. Normal mirrors reflect about 95% of light, while reflecting prisms reflect the light totally, TIR. This is important for several applications such as periscopes, rear reflectors, and binoculars. For a better quality for those applications, TIR is needed, and to achieve TIR, you need physics. Another important application are optic fibers. Optic fibers are thin, flexible rods made up from special glass, and as light passes through those fibers, it gets totally internally reflected. As light enters one end of the optic fiber, it hits the boundary between glass and air. If we draw a normal line, the angle of incidence is more than the critical angle. Therefore, total internal reflection will happen as shown. And then it hits another boundary. So if we draw another normal line, still the angle of incidence is more than the critical, and total internal reflection would happen. This process will keep on repeating itself for hundreds of kilometers until the light exits from the other end. It depends on the length of the rod. Sometimes optic fibers could reach hundreds of kilometers. So what's the benefit of those optic fibers? Well, the most important application is the use in communication to send signal light, such as internet. So to understand what's happening, this is just an overview. If this router over here sends a code of 1010, now what does this signal mean? It just means that you switch on the light for a while and then off and then on and then off. 1010. One means on, zero means off. The pulsating light signal can be understood by the receiving end, the other end of the optic fiber, as something else, a representation of something. For example, 1010 could mean the letter A. If this signal was sent from one end to another, the receiving end will understand it as the letter A. Maybe for the letter B, it's 1001. And when that signal reaches the other end, you understand it as the letter B. This is how data is transferred in bits. More discussion about.
Did you understand, Mohammed, what's happening in telecommunications here from Wi-Fi to the other end?
Yeah, it's like sending a communication,
Yes. What does 1010 represents in this case?
which means like light is on for a while, then off, then on, then off. Then
Yes.
it's
Yes. Okay.
it's like
So
one zero one. One is on, zero is off. One is on, zero is off.
what is this called? This is called as bytes, data, anything, right? Are you studying computers?
No,
Okay,
no,
so this is
unfortunately.
like a binary system where it just represents, okay, one represents on or yes, true also, one true, zero false, like that. Okay, so it just sends the data from one end to other end by using optical fibers. That's how when you are installing router, all right, so there are many wires inside this which connects, to the other end because it needs to carry information. So optical fiber will basically carry information and send signals from one end to another end. In which form? In the form of binary codes. That is 10. We're going to use it. Is it clear, Mohammed?
Yeah.
Okay, so that's it about total internal reflection. Okay, and refraction also we have understood. Okay, now coming to sound. Okay, before I could start the topic sound, okay, I would like to ask you a few questions here. All right. And I want to show you that video over here. So sound is the last part of this chapter. How is sound produced, Mohammed? You're able to hear me. How is that?
Just through like I don't know what to call it, speakers,
Through speakers. Okay.
through megaphones,
Through megaphones. Correct.
like the picture that's showing.
Yes. So basically, what's happening is there is disturbance in the medium, right? If there is a disturbance in the medium or the medium vibrates, then sound is produced. So for sound to produce, there has to be some vibration or some disturbance. All right. Now, for example, if you just tap any hard objects around you, top, if you just tap it, you're going to hear something, right? Some noise. So basically, the solid, the molecules present inside the solid, all right, it starts vibrating in its mean position and releasing sound. Okay, we shall discuss about that. So the beginning and the introduction of sound is sound waves are longitudinal waves and not transverse waves like light. Nevertheless, they can be reflected and refracted in just the same way. Okay, so sound also follow the same principle of light, that is reflection, refraction, and absorption up to some extent. In this chapter, you will learn about the nature and behavior of sound waves and how we can make use of them in our everyday lives and not just when we talk. Okay, no sound waves getting in here, so no homework. So using sound waves to communicate. Okay, and what is the reason for this, Mohammed? They are closing their ears, isn't it? And this person is speaking over this loudspeaker. You know what's happening here? So basically, okay, my question to you, are they able to understand what the teacher is saying in this case? Are they able to understand?
Yeah, I think they understand. I think it's an oscillop. I'm not sure.
Okay, the teacher is speaking here and they're closing their ears. They're not able to understand what the teacher is speaking. The reason is because it is above human hearing, isn't it? So for us to hear, we have certain range, which is basically 20,000 kilohertz is the range where human beings can hear. If it, so I think, yeah, 20,000 hertz. If it is, if it is above 20,000 hertz, in this case, you can't hear. That is ultrasound where bats produce. That's how they're able to detect objects. We'll study about what are those ranges. Okay. Now, just a brief introduction about this. Uh, in figure 13.2, the sound produced by the speakers must be loud but also of good quality. Okay. So this shows part of the sound system used by a band playing at a concert. This equipment must produce sounds that are loud enough to be heard by all the audience, and the sound quality must be good enough for the music to be appreciated. In this chapter, we are going to look at how sounds are made and how they travel as waves. So they travel as longitudinal waves, all right, and how they are produced. So basically, sounds are produced by objects that are vibrating. We hear sounds when these vibrations traveling as sound waves reach our ears. All right. So how are they produced? They are produced by vibration. When vibration is caused, sound is produced. And they travel in which form? They travel in the form of waves called as sound waves.
Yeah.
And we can hear the sound on reaching human ears. Okay. Now, uh, so compression, rarefaction. Okay, basically I don't want that. Okay, now measuring the speed of sound. How can we able to measure the speed of sound? So this is the investigation to measure the speed of sound. So you can measure the speed of sound using two bits of wood and a stopwatch. Some stand some distance away from a friend. Start the stopwatch when you see her bang the two bits of wood together and stop the stopwatch when you hear the sound. Now use the equation. V is equal to distance by time. You can calculate the speed of sound. The answer you're likely to get will not be very accurate unless you have very good eyesight and very fast reaction. Okay. All right. Now, Mohammed, you are going to just do one experiment. All right. The experiment is very simple. So there are two people. One is one person A, other person B, standing at the two ends. Okay. One person is going to record the timings, okay, by using a stopwatch. So there is a stopwatch, this is a stopwatch. So when this person is playing some band, okay, some kind of a band over here, so when these two collide, then sound is reaching. So basically
Yeah.
sound is reaching to this person's ears. All right. So what's happening over here? So to calculate the speed of sound by using the equation, v is equal to, speed is nothing but speed is equal to distance by time, isn't it?
Yeah.
In this case, Mohammed, can you tell me going one distance, coming back another distance, that is reflection. So there will be
Yeah.
twice the distance in the case of reflection of light, in the case of reflection of sound. Okay, so that is the topic that we're going to discuss, okay, in the next class. Okay, but in this just an activity, both of you and your friends should stand at least 50 meters away from a large wall or building. Bang the two pieces of wood together and listen for the echo. What is the meaning of echo, Mohammed? Have you heard about this anywhere?
Like that.
What is
It's like it's like something that's, I don't know, like repeats itself many many times. When I bang something like in a basement somewhere, it's like repeats and repeats. The sound repeats and repeats and repeats.
very good? So repeating is called as multiple reflections. So when multiple reflections take place, we can able to hear the echo. It usually occurs, as you mentioned, in a compact place like a basement, or even the case of mountains, the top peak of the mountains. You can able to scream loudly and you can hear your own voice after 1 second, isn't it? So that is the echo, reflection of sound. Okay, so bang the two pieces of wood together each time you hear the echo. This will create a regular rhythm of claps. Ask the friend to time you doing 20 claps. So when you're going to do 20 claps during this time, the sound will have traveled. For example, 50 meters you're standing, then 20 times you're clapping, and two. Why two? To the wall and back 20 times. Okay, so to send and to receive. That is why they are using two. Did you understand here why they using two?
Yeah.
Right, the sound will send and it will receive back. That's why they're going to multiply 2 into 20 times into 50 meters, and you can divide the distance by the time you are going to work out for the speed of sound. So the next class, Mohammed, we're going to just look into the last topic of sound, and let's finish this off. All right, Mohammed.
All right.
Okay, then if there are no questions, then I will see you in the next class tomorrow for mathematics. All right.
Okay.
Okay, take care,
Well,
have a good day. Bye bye.